Okay, so what today's lecture was really supposed to be about was no longer about developing brand new algorithms for flow and edge disjoint paths, but using the algorithms for flow and disjoint paths and actually seeing all these different kind of creative applications that you can address. Okay, so all right, so here I have slides for all these different things. Apparently, I was inspired to draw circles around all our topics. But anyway, okay. All right, so here's okay, so everything in today's lecture is really going to be about reductions and some clever ways to transform just completely different applications into flow problems. Okay? So the way I've organized it is as follows. So a lot of these are actually quite guessable. So what I'm going to do is I'm going to go through the problems twice. On the first pass, I'm just going to introduce the problems, what they are and what they're trying to do, and give you some time to kind of soak it in. And then afterwards, we'll go back through and we'll solve them one by one, and hopefully you guys will guess at least a few of them. So, okay. Vertex disjoint paths we've already done, so I'm not doing that. All right, here's the first one. All right, bipartite matching. So bipartite matching, you're given a bipartite graph. That means that the vertices can be split into two parts so that all the edges go from one part to the other, just like the picture. A matching is a set of edges where the endpoints don't touch. Okay, so you want to take as many edges as possible that don't intersect each other. You want them to be completely separate. Okay, so like, I don't know, I'll give you guys a chance to stare at this and see how big of a matching you can find. So the goal is to take as many edges as possible so that they're not overlapping at any endpoints. 5? Okay, can anyone do better than 5? 6? Anyone else get 6? 6? Okay, we got some 6s. Okay, I guess what I'll do is I'll like highlight some edges and you just tell me whether I should take it. Okay, so I'll start with the top one. I don't know if you guys can tell. Yeah. Should I take this edge? No? Okay. Um, should I take this edge that's kind of going diagonal? Okay, you want that one. Okay. How about this edge? Okay. So this edge we can't take anymore because it's already incident to one red edge. This edge we also can't take anymore. That edge can't take. All right, so next, that edge I also can't take. All right, so what will be an interesting choice? Okay, this one. Do you want me to take that edge? Okay, I saw some no's. How about that one? Okay, strong yes from the right. How about this one? Okay. Uh, this one we cannot take anymore. This one we cannot take anymore. That one we cannot take anymore. That one cannot take anymore. Cannot take anymore. All right. How about that edge? Okay. And then I guess is the only edge left to take. Okay. Good. So that's 6 edges, and they're disjoint at the endpoints. They're crossed in the pictures, but that's irrelevant. That doesn't count as overlapping. Okay. All right. So maximum set of edges, distinct endpoints. I guess I had. Okay. All right. So that's bipartite matching. We're going to try to figure out how to solve that with just flows and cuts. Here's another problem, sort of a dual problem. So in this problem, your goal is to choose vertices and as few vertices as possible. But the rule is for every edge in the graph, and again, it's a bipartite graph, you have to choose at least one of the endpoints. So I want to choose a bunch of vertices, but as few as possible, so that I'm touching every edge. Give you guys a chance to stare. Okay, so if you choose everything on the left, that would give you 6, right? So this would be an example of 6. Can anyone do better than 6? Because it doesn't have to be all on one side, right? Maybe you can mix them up in some clever way. Anyone do better than 6? The bottom one? Oh, but now this edge is not covered. The bottom edge is not covered. If I just delete it. This edge here, we haven't chosen any of the endpoints. Okay. So this is actually the same graph as from the matching problem. The answer is actually 6. You can't do better than 6, but can anyone actually explain why? You can actually argue that this is the best answer. How come you can't do better than 6 for this case? Yeah. No, if I had drawn a more interesting one, it's quite possible that maybe we would have chosen like 3 on the left and 2 on the right or something. Yeah. In this version, it's kind of boring that it's just all on the left. Yeah. So this is the same graph as before, where we're able to come up with 6 independent edges, right? So from each edge, I'm going to have to choose at least one of those vertices, and they're not overlapping. So the size of a vertex cover is always at least the size of any matching. So in this case, we can actually certify that 6 is the right answer. Okay. That also means that if it was less than one side, that means there must have been like a smaller matching as well. Okay, good. All right, here's sort of a funky problem that I always cannot believe can be solved by flow. So I guess imagine that you're a construction company or something, and you have a bunch of projects that you can choose from. Okay, and each project is associated with some kind of profit, or a negative number would be a cost. Like I build this, it'll just end up costing me $10. If I build this, I'll make a net profit of $20. Something like that. So the positive numbers represent kind of projects that are net profits. Negative numbers represent things that are really cost. So why do I even have costs at all? We're also going to have dependencies. If I want to do this really profitable project, I have to do some expensive projects first or something like that. So I've drawn purple edges to map dependencies so that 4 requires doing a -2 and a -3 just to build the 4 and stuff like that. On the other hand, there's some interesting stuff going on because some of those costs can serve multiple projects and stuff like that. So, maybe there's some selective way to choose some of the projects while containing all the dependencies to maximize the profit. Okay. All right, so what's the best score you guys can come up with this one? Okay, so you liked 462 and the corresponding dependencies. All right, so 12 minus 10, so that gives you a score of 2. Can anyone do better than 2? Yeah, just 4 and 6. Okay, well, once you take 4 and 6, you also have to take 2 because 6 depends on 2, and you end up having to take the same ones anyway. So you have to kind of like follow all the purple lines and take any project that you're dependent on. Okay. All right. So the model makes sense? All right. Okay, so that's another problem that we'll do. Okay, next one is playoff elimination. So the idea is this isn't really realistic because, well, I think this is okay. Boston's not very good anymore. Anyway, right. Okay, so imagine you're a baseball team and you're getting close to the end of the season, and your goal is to make the playoffs, and you're really close, right? Maybe you're like only 2 games out of first place or something. But even if you win all of your games, you have to hope that other teams will win or lose or something like that, right? So like in this example, um, Boston is 2 games ahead out of tying for first. Maybe the goal is just to tie for first. Okay. But so in principle, if the Yankees lost if all the other teams lost all their games, and then the Boston Red Sox won both their games, they could be tied for first. Right? So that would be kind of simple. You just subtract and add. But it's more interesting because maybe these teams play each other. Right? So if they play each other, then you can't just assume they're all going to lose all the time because somebody has to win. So maybe the full data looks something more like this. So uh, so here I've just written 1 because New York still needs to play Baltimore once, right? And then New York also needs to play Toronto once, and Toronto needs to play Baltimore once, and Boston needs to play both Baltimore and Toronto once, right? These are the remaining matchups between the teams, right? So now the question here is, if these were the remaining games, is it possible for Boston to make the playoffs? Okay, no, why? Okay, maybe it's hard to explain, so maybe I'll walk through it. So let's say let's say that I might as well award all the wins to Boston, right? And then so Baltimore and Toronto aren't going to get those, so that gives it 92. And now for Boston to tie New York, I need to make sure that New York loses both its games. Okay, so New York will not get either of those, and I'll give this one to Baltimore and this one to Toronto. So now Baltimore and Toronto each have 92 wins because they beat the Yankees. But we still have this game between Baltimore and Toronto, and whoever wins is going to end up with 93. So the Red Sox are screwed. Okay. All right. Okay, so that kind of problem we'll try to solve. Any questions? Okay. All right, here's another problem that actually I think motivated a lot of research into this problem a long time ago, back when I think in like World War II they were trying to figure out how to efficiently allocate people to boats and stuff. But it's just like an assignment kind of problem. So in this story, but it can be all sorts of different setups. You have a bunch of people and you have a bunch of jobs. You want to fill up all the jobs with people. Okay? But the only catch is that not everyone is qualified for every job. So person A might be able to do some jobs, but not other jobs. Okay? So your input might include some kind of, in the original paper a long time ago, they called it a qualification matrix. And it just has a 1. So the rows correspond to people, the columns correspond to jobs, and there's a 1 if the person fits the job, fits the square, and a 0 if not. Okay, and the goal is, can you find a way to assign people to cubicles accordingly? Okay, that's an assignment problem. All right, here's a fun one. Edge orientation. Okay, so in edge orientation, you're given an undirected graph, okay? And your goal is to direct all the edges. So for every edge, I'm going to pick a direction. Like maybe I'll direct that edge this way, and this edge that way, and stuff like that. So I'm going to I'm going to point every edge. And my goal is to direct the edges to minimize the maximum in degree. Okay, so I want to direct all the edges to minimize the maximum in degree. Okay, so since might be hard to describe a solution, so like this might be a candidate solution, which I guess is able to get what is this, 3 maybe? Yeah, okay. Anyway, something like that. Okay. Um, good. All right, so okay. And then the last application I have set up for us is called densest subgraph. This is popular in like studying social networks and stuff. But in general, for a graph, the quote unquote density is a ratio of the number of edges divided by the number of vertices. So that's m divided by n. But the goal is to find a subgraph, so a subset of vertices. Like if I looked maybe at these 4 vertices on the right, and I only look at the edges contained in those 4 vertices. Right, so that's 1, 2, 3, 4, 5. The density of that subgraph is 5 divided by 4. There's 4 vertices and 5 edges. So the goal is to find the densest subgraph in the graph. So if you're studying social networks, they might think of that as like a tightly knit community or something like this. In a communication network, some kind of anomaly or something. Anyway. Okay. Yeah, I mean, what's the densest subgraph you guys can find in this graph? Okay, I did plant a click in the middle of this graph, which I don't really know if it's a dentist, but I figured it probably is. Okay, so, all right. Okay, so I think that's all the problems I had for us. And now we have 30 minutes to try to knock as many as we can out. Okay, whatever we omit, of course, is in the notes and stuff like that. Okay. All right. All right, bipartite matching. So now the goal is to find a maximum set of edges with distinct endpoints. So here, for example, is an example of a matching, right? Okay, so, all right, how can I try to find a large set of disjoint edges with flow or edge disjoint paths or minimum ST cuts? That's the question. Yeah. Source on one end, sink on the other. Okay, so I think this is what you're saying. Okay, like that. Now we need well, if you're doing, we need to assign capacities. So what capacities would you assign? Okay, one's everywhere. And are you going to do anything about the middle edge? Like, do I want to treat that as both directions or maybe just one direction? Okay. So we'll direct all of them from left to right. And you can give them all capacity 1 or infinity, it doesn't really matter. Okay. All right, so now when I route flow or an integral flow, so one thing worth pointing out, if the capacities are integer, then the max flow will also have integer values. You can assume it'll return integer values. So for this, it'll always be 0 or 1. You don't have to worry about weird point twos and stuff like that. So, okay, so every path from left to right, basically has this form. You can't zigzag or anything because all the edges go from left to right. So they're really just defined by what edge you're using in the middle, right? For every edge in the middle, there's a unique path from S to T that uses that edge. So there's a nice one-to-one correspondence in this graph between the path from S to T and the edges in the middle. Okay, so that's good because then, like trying to take lots of paths is like trying to take lots of edges from the middle. The only thing is they have to be, endpoints have to be disjoint, right? It's supposed to be a matching. So how are we enforcing that in this construction? How come I'm not able to take two edges with the same left endpoint? We can't have well, so I think so if the flow told me to take this edge and that edge, for example, right, this would not be a matching. The only way to do that, the only way to get there is with this one edge from S to the left endpoint. Okay, but we can only send one unit of flow. Yeah, we already set it to one. Oh, but we want one. So, okay, because we set it to one, we can't have, so this is bad, right? We don't want edges that have the same endpoint from your point of view, like this, right? Because then it's not a matching. So by putting that capacity of one from the source to that vertex, I guarantee there's only going to be one path using that vertex. Yeah. Yes, yes. For integer capacities, you can always assume integer flows. Yeah, I forgot to make that point explicitly. Yes. I think we're all on the same page. So integer flow means all the values are integers. In this case, the capacities are one, so the only values you have at your disposal are 0 or 1. Yeah. Okay. Or you could run edge disjoint paths. But anyway, um, okay. So the capacity of one on the source and sink edges are that's where you really encode the fact that you can only use each endpoint once. All right. Good. Right. Okay. So matching with k edges if and only if there's k edge disjoint paths. All right. And I'll go relatively quickly, and then in the notes you'll find long, thorough paragraphs going both directions of the proof and stuff like that. Okay. So this one might be a little trickier. A bipartite vertex cover. So remember the goal here is to choose as few vertices as possible to cover all of the edges. How can I try to solve this with max flow or min cut or edge disjoint paths? Max cut or min cut? Okay, min cut of roughly the same graph as before. Okay. All right, I'm redrawing the same thing. I'll just draw some of the arrows and then let you use your imagination for the rest. I'm going to make one small tweak, which we could have done for the last one, is that instead of having capacity 1 in the middle, I'm going to have capacity infinity, or essentially unbounded capacity. Okay. All right, so now let's look at any ST cut in this graph. So I have the same ones on the source and sink edges, and then like really large capacity in the middle, infinite capacity in the middle, right? Now suppose I have some kind of way to partition the vertices where S is on one side and T is on the other. So I'll draw like, well, this is not a good example, but like this could be the boundary of one ST cut, right? There's some vertices on the S side and there's some vertices on the T side. Okay? And right. Okay, so this is not a good example because it yes. Um okay, so one sec. This is a bad example because well, okay. Let me do one thing. Okay. So this picture is a little bit misleading because of the infinite edges. We would never cut any of the blue edges because that would destroy our min cut. So what I'm going to do just to make it interesting is I'm going to erase those edges that are um, cut. Okay, so that's okay. So one thing important is that we're only interested in the edges that are leaving. Let me use a highlighter here. Uh, that's not great. Okay. All right. I'm only interested in the edges that are leaving that side of the cut. So now that I've erased a few edges, there are no blue edges that are leaving that side of the cut. Okay. Now let's look at the okay. So because the blue edges are in the middle, are infinite, okay, the only edges that are cut are going to be some source edges and some sink edges. Okay, those with capacity 1. So let's look at those vertices that are cut. So I'll circle them. This is cut, right? I mean, the source edge for those vertices are cut. And on the sink side, the sink edge for those vertices are cut. Okay, so there's a cut of size 5 that corresponds to the source or sink edge of 5 vertices. Okay, because those are each worth 1 point. Okay, what do you notice about the circled vertices? They form a vertex cover. So every edge is incident to one of these vertices circled in red. Okay, so every ST cut will correspond to a vertex cover Y. Well, let's look at a particular edge. Like, I don't know, this one, for example. All right, let's look at an edge like this one or something, right? Now, in this picture, I do cut one of the endpoints, right? I'm cutting the source endpoint. But suppose I didn't. right? So if I have an edge and I'm not cutting the source edge and I'm not cutting the sink edge, and I'm definitely not cutting that edge itself because it's infinite number of points, then I have a path from S to T, right? From the source through the edge to the sink, right? So I have to cut off one of the ends of every edge to make sure there's no path from S to T. Okay, so every S to T cut must give rise to a vertex cover. That's the only way to disrupt all the paths from S to T. Conversely, I want to argue that if I had a vertex cover, right? So if I first just had 5 vertices like that formed a vertex cover, I would be able to look at it and say, oh, those will give me an ST cut. Okay. So how come every vertex cover will give me an ST cut? Well, if I look at any path from S to T, right, I need to make sure that I break every path from S to T, right? And all the paths in this graph have a very simple form. They go from the source to some left vertex, across the middle, and into the sink, right? That's how all the paths look. And because it's a vertex cover, I know I'm taking either the left or the right endpoint, and then I'm going to be cutting either that left or right edge. Okay, so from a vertex cover, given a vertex cover, I delete the corresponding source and sink edges, and that gives me a cut, and it'll disrupt all the paths. Okay, so we have this one-to-one correspondence between vertex covers and ST paths in this bipartite graph. Okay. All right, so the minimum ST cut will give you a minimum vertex cover. I always find that the applications that require ST cuts are a little bit trickier to wrap my mind around than the flow ones, but we'll get some practice. Okay. All right, here's, I think, the most non-trivial one. Well, maybe a relatively non-trivial one. All right, so this is that project selection problem. My goal is to choose a lot of projects that includes all the dependencies to maximize the net profit. Okay, and I want to try to solve this with max flow or min cut or edge disjoint pass. This one's hard to guess, but I'm still going to give you guys a chance. Any idea is fine. Silly ideas are fine. It's more fun that way. Yeah. Okay, so like for example, you're saying that maybe I can like say, oh, this is 6 and this is -3, so maybe I'll give this capacity 3. Um, yeah, oh, okay, there's lots of questions to be addressed. For example, here's 1, 6 and 1, 2. Do we give that capacity 8? Okay, and then here's 1, 2 and 1, -5. Do we give this capacity -3? Well, what does capacity -3 mean? Like a what? Split the vertex? Uh, okay. Well, okay. So actually, max flow actually won't quite get us there. It won't actually be max flow. We're gonna actually try to do a min cut. approach. Um, Anyone want to try to guess how? Oh, okay. Do we send an edge this way of weight 3? Uh, I mean, I guess anything is possible. Uh, yeah. But it's not clear what the edges mean. I just feel like we're just like guessing capacities and adding up nearby numbers and uh hoping for a miracle. I mean, I guess probably the eventual thing will seem somewhat miraculous, but all right. At least the point that this is non-trivial, I think, has sunk in. So let me explain the construction. Okay, so here's what we end up doing. So we make a super source and a super sink. For every profitable project, I add an edge from the source to the project, um, where the capacity is equal to the profit value. And for every project that's a cost, that's a negative number, I make an edge from that project to the sink with a capacity equal to that negative number negated, kind of the cost as a positive number. Okay, so you see like -2 now has an edge to t of capacity 2 and so forth. And the dependencies we treat as edges with capacity positive infinity. Okay, so that's what the setup is going to be. Okay, so, okay. Um, right. So, okay, so the claim is that a minimum ST cut, and in general, trying to find small ST cuts will give us better project selections. Okay, so let's try going through an example. So if I looked at a cut defined by, I use blue. Uh, okay, so maybe all the edges that are, yeah, let me draw that again. Okay, so on this side, okay. All right, so if I separate out those vertices, then whatever edges are going across from left to right, that'll be my ST cut. And that separates S from T, or S from T from your point of view. Okay, so let's look at this example. So first of all, you know, okay. So, all right, so what is the value of this cut? So this cut, the value is, we have 1, 3 here, right? Plus a 2 here, and a 3 here, and a 5 here. Okay, so what I want to do is I want to imagine the source side of the cut as the projects I take. So in that example, we're taking 4, 6, 2, -2, -3, -5. Okay, which was the suggested solution from before. And okay, and what is the cost of the cut? The cost of the cut is, first on the right, we're adding up the costs of our expensive projects, right? The -2 to -3 to -5, 2 plus 3 plus 5. Okay, and we also pay the cost of any profitable project we leave out. I leave out 3. Okay, so this at least makes some sense, because in general, I want to minimize all those negative costs, right? So that 2, that 3, that 5, that's bad, and I want that to be small in a minimum ST cut, just like I want the expenses to be small in a project selection. And on the left, this 3 is the amount of profit I'm leaving on the table, which I also want to be small. I want to get all the profitable projects ideally. Okay, so we can at least see directionally that the minimum ST cut will want to take lots of profitable projects and will want to minimize the number of expensive, costly projects it takes, or the quantity, or the total cost, I mean. Okay, so two more things to point out is that, so when I'm worrying about the edges that are being cut, I'm only worried about the edges that go from the source side to the sink side. So it is true that there is a purple line going from 3 to 2 that goes across the blue line. But that's going from the sink side to the source side. So it doesn't count as part of the cut. Right? Because if I took all the edges that are leaving the source side and going to the sink side and I remove them from the graph, then I can't get from source to sink anymore. The edges going back from sink to source don't matter. I'm only worried about making sure source cannot get to sink. So it's okay that we have a purple edge coming in. But you also bring up another point. If I, once I chose like the project of value 4 up on top, then I have to take all the dependencies. And I don't want to cut those edges because that'll be a cost of infinity and I'll just lose right away. Right? So by making the dependencies infinite capacity, the minimum ST cut will never want to cut those edges. And that'll force us to take all the dependencies. Okay. So, alright, so just to formalize this, I think now we sort of see intuitively what's going on. But if we wanted to write out the math, it would be something like the cost of the cut is equal to the cost of, I guess I'll call it bad projects, the red projects taken. Maybe I can put this in red. Oops, not that. Okay. Plus the profit of good projects omitted. Right? So we left out that project worth 3, and so I paid $3 in the cut. Okay. And this is equal to, let me duplicate this to save time. Oh, it doesn't fit. Okay. All right. So this is equal to, I guess, the total profit of all the good projects minus the profit of good projects taken. Right? So all I'm saying is that 3 is equal to 4 plus 6 plus 2 plus 3 minus 3. Oh, no. 4 plus 6 plus 2 plus 3 minus 4 plus 6 plus 2. Okay. Whatever. The point is that there's a fixed total amount of profit out there, right? In this picture, it's 15. And the profit I leave on the table is the total out there minus the amount I get. Now, the total amount out there doesn't change. That's like a fixed quantity, right? So all that's left then is that the minimum cut is trying to minimize this difference. It's trying to minimize the cost of the projects taken minus the profit of the projects taken. Okay? And if I want to turn that into maximization, that's maximizing the profit of the projects taken minus the cost of the bad projects taken. Okay, so minimizing the ST cut is maximizing the net profit. All right. Okay, any questions? That was one of the harder ones. Let's see what's next. Oh, we only have a few minutes. All right, playoffs. Um, does anyone want to quickly try to guess how to do playoffs? You only have a couple minutes. All right, time's out. All right, here's the idea. We have a source and a sink. So what I've done is I made a vertex for every game that's left. Okay, and teams. Okay, so there's like I want to think of this as allocating wins. So one unit of flow is like allocating a win. So the game between New York and Baltimore can either go to New York or it can go to Baltimore, right? And the game between New York and Toronto can go to New York or it can go to Toronto. Baltimore and Toronto can go to Baltimore or Toronto. Baltimore versus Boston can go to Baltimore or Boston. Toronto versus Boston can go to Toronto or Boston, right? So on the left, it's saying, okay, I can send one unit of flow and I have sort of one win to give out, and it can give it to one of the two teams. Now, based on that playoff picture, there's a limit to how many edges I can give out, wins I can give out, right? So New York, I don't want them to win at all because New York was already 2 games ahead of Boston. And Baltimore, they're allowed to win 1 game each before they got to 92. And in Boston, I want them to win as much as possible, so I won't put any capacity, right? So I'm trying to allocate wins, but I've put a limit on how much each team is allowed to win. And if I'm able to allocate all the wins while obeying those limits, then there is a way for Boston to get there. If I can't, then Boston cannot. And I can do the proof more slowly, but there's no time. Okay? But the idea is we're allocating wins. All right. Great. Nice and fast. Okay, I want to try to knock all these out. So, how about this one? This one you might be able to guess. You're assigning people to jobs, but not all people are qualified for all jobs. How do we solve this? Yeah, so this is really just a bipartite matching problem where I have an edge between a person and a square if the person fits the square. Okay, and otherwise, taking an edge is like taking an assignment. Okay, so that actually motivates a lot of early studies into matching problems. It's like matching is like such a applicable problem. Okay, all right, we're almost done. We'll go a little bit over, but I'll try to make it quick. All right, edge orientation. Here the goal is to direct the edges to minimize the maximum in degree. I'm going to make it a little bit easier and look at the decision version of the problem. So that means I'm going to give you an undirected graph and input, and I'll give you some parameter h, like 5. And say, okay, can you direct all the edges so the maximum in degree is at most 5, or in general at most h? Any ideas about how to do this? Not quite. Anyone else want to guess? Well, think of it this way. For each edge, right, it needs to pick one of the 2 endpoints. So each edge has to pick one of the 2 endpoints, and each endpoint can only be picked h times. It's sort of like an assignment problem. I'm assigning each edge to one of its 2 endpoints, but I don't want any endpoint to get assigned too many times. So we can do something like this. We create a bipartite graph. On one side, I sort of have one vertex representing each edge in the graph. On the other side, I have one vertex representing each vertex in the input graph. And I draw edges saying, okay, this edge can be assigned to one of the two endpoints, right? And on the right, that capacity of H, so the capacity of 1 on the left is saying each edge I want to assign it to one of the two, right? And you get to assign 1. And on the right, the H is saying I can only have in degree H. Each edge can only be assigned, each endpoint can only have H edges pointed in. Okay. All right, last one. Densest subgraph. Okay. Here the answer might be something like this. And we're going to do the same simplification where given a parameter h, I want to know if there is a subgraph of density greater than h. So if I gave like h is 2, or something, I don't know. I think that subgraph has density more than 2, but maybe it's exactly 2, so it's okay. All right, anyway. Okay, any ideas for this? Okay, I think the only idea is how do we get out of here fast, so I'll just go. Same idea as before. I'm going to make sure we have infinite capacity in the middle this time. Okay? And what will happen is that if there is a dense subgraph with density bigger than h, okay, then what will happen is that you have an ST cut that's sort of, okay, I'm only going to do it quickly and I'll write something in the notes. But roughly you look at the ST cuts and see which vertices are, I think, on the S side. Okay? And then you work through it and you can show, okay, these have to be pretty dense because at some level I wasn't able to allocate all the edges inside this graph in such a way that there was at most h per vertex. Okay. I'll sort out the details in the notes, but that's the basic high-level idea. It's the ST cut analog, kind of the opposite of the edge orientation problem. Okay, I'll just end it there. I'm over time, and okay, those are all the applications, and there's lots of fun problems in the back of that chapter for more reductions. All right, thanks, guys.